solution concentration units. Now that's what the rest of this chapter is about. We have lots of different concentration units in play because there's a lot that you're going to be exposed to and working with in your life. And we're going to start with molarity, right? Now, all solutions are given in concentration as amount of solute divided by the amount of solution, or I should say most of them. All the ones that we talk about are going to be given this. We just have different units for different concentration units overall. But chemists, and this is the one that you're going to need to know first, and it's the one that we're going to continue using in chapter 10, so you're going to really need to know it, is we use molarity. And molarity is given the amount of solute is in units of moles. Moles of solute divided by, on the bottom we have liters of solution. And I did say, for the rest of this, we're going to be talking specifically about liquid solutions. And so we're going to be measuring that liquid in liters. So the number of moles of solute in liters of solution, or moles per liter, is molarity. So for instance, we can use, it's really easy actually, we just use dimensional analysis to solve these, and it's quite simple. Here's a very simple example from the lecture notes. We'll say, calculate the concentration of 0.34 moles of hydrochloric acid in 1.5 liters of solution using units of molarity. This tells us, just dimensional analysis says, look, if I have moles of solute on top and liters of solution on the bottom, I've got this. So I'm going to do exactly that. I'm just going to say, there's my moles of solute. There we go. Here's my liters of solution. Putting that there. And when I plug this in, I will get moles per liter, or molarity. There we go. 0.034 divided by 1.5, 0.0227. And molarity has the shorthand of a capital M. Capital M means molarity. Molarity means moles per liter. So that's when you see that capital M, HCl, that is saying this is a unit of concentration for HCl. Does that make sense? Great question, Sarah. Why don't we just keep it as moles per liter? I don't know. I think they wanted an easier thing to say. So you could say I have a 0.03 molar solution of HCl instead of 0.03 moles per liter solution of HCl. You have to do that. It is more difficult because then you have to do that translation, right? You see this, you should automatically and quickly replace it with moles per liter, right? And you should do that because everything else we're doing here is going to be dimensional analysis, and you can't do dimensional analysis without these dimensions, right? These dimensions are kind of important for the dimensional analysis, whereas this capital M is hiding those dimensions. Does that make sense? So I tell students, I say, listen, when you are working with molarity, you should always quickly replace it. And when you see molarity, you should think moles per liter. And when you write molarity, you should write moles per liter. And if you are in the test, and this works great for you guys because you're at home, right? When you're in the test and you see a capital M, you should just shout it out, moles per liter, because this is the most common place to get hung up on one of these problems, because you just can't solve the problem with a capital M. You have to convert it to moles per liter first. All right? So for instance, if instead I give you grams, or if instead I give you milliliters, you're going to have to do dimensional analysis and convert, right, to moles and liters to get that. In fact, I think that's on your worksheet. Here, let's do that. Molarity. I'm going to pull these up from the worksheet, and you can help me solve these problems. So for the first one, how am I going to solve this molarity of a solution with 1.25 moles of glucose and 5.40 liters? Good, yeah, you're just going to plug it in, right? Again, you're going to be like, hey, there's my moles, done. There's my liters, putting them where they go. And then, haha, I have moles per liter. So 1.25 divided by 5.40, that gives me 0.231 molar, and this is glucose solution, right? Okay, not so bad. What about this guy here? Oh, look at me. I'm so rude. I gave you grams, but you need moles. And to go from grams to moles, you need the molarity. You need the molar mass. So then we have to pull out our periodic table, which isn't actually so bad because then we can feel like we're actually like doing chemistry, right? Doesn't feel like chemistry unless I have a periodic table handy. All right, calcium's 40.08 grams per mole. And then I had 2 nitrates, right? So that's 2 nitrogens. And then NO3 gives me 6 oxygens. So plus 6 times 16. Is that NO3 Did I do that right? Oh, yes. All right, so I'm getting 164.1 grams per mole for calcium nitrate. Do you guys agree with that? Okay. So now what do I do? How am I going to get moles divided by liters? All right, I think Sarah's got a good setup. She says, look, if I take 4.75 grams of calcium nitrate, and then I divide it by the molar mass here, we'll have 1 mole of calcium nitrate in every 164.1 grams of calcium nitrate. Perfect. If I do that first step, then my grams of calcium nitrate cancel, and I'm left with moles of calcium nitrate. That's just what I wanted, the moles of that solute on the top. Now I just need to put the liters on the bottom, right here, 0.200 liters. Stick it on the bottom because that's where I want it to be. And again, I don't need anything on top here any more than I needed anything on the bottom here. I get to choose where these units go to get the answer in the units that I want. So 4.75 divided by 164.1 divided by 0.2, and what do I get here? 0.145 molar solution. Is that what you got? Of calcium nitrate. Okay. What about, let's do this guy down here. We're going to need the atomic mass units because I was given grams and we need moles. Okay, so 2 times 12.01 plus, I've got 6 times 1.008 plus 16, 46.068 grams per mole. Okay. Oh, good. We're going to need to convert milliliters to liters because, again, I need specifically moles on top and specifically liters on the bottom. So to do that, I'm going to remember 700 milliliters and I have 1 liter is 1,000 milliliters. right? So that's going to equal 0.7 liters. Okay. Now, Sarah says, starting with what I was given, 0.825 grams C2H6O. And we're going to say 1 mole of C2H6O has got 46.068 grams C2H6O. C2H6O, that's drinking alcohol, by the way, ethyl alcohol. So my grams cancel, and I've got moles on top. And so now we're going to put the liters on the bottom. Here we go. 0.825 divided by 46.068 divided by 0.7, and I get 0.026. All right. Molarity C2H6O. Is that what you guys got? Okay. These other problems are basically the same. You guys feel good about these? Okay. What if we went backwards? So here we go. This is the next section. Still doing molarity, but now I'm asking for grams of solute. Let's do this one for funsies. Grams of solute in a 50 milliliter solution containing 0.360 molar concentration of, looks like potassium dichromate. How would I solve this guy? Huh? Okay. Oh, perfect. I'm so glad that that was the first thing that you did, Sarah. Sarah says the first thing I'm going to do is remind myself that that little guy is moles over liters. Excellent. Because I'm going to need that. Okay. And then the second thing Sarah says is, since I have liters here, I'm going to need liters. And I'm not going to bother doing an whole dimensional analysis chain. I'm just going to convert that right now to 0.05 liters. Maybe you did that. 50 divided by 1,000.05. Okay. All right. So she doesn't have to do a whole chain. She can just kind of piece it together here. And now she notes I'm going to need the atomic mass units, or the molar mass, of K2CR2O7, because here I've got the number of moles in a liter and I know the number of liters, but they want the grams. So here we go. K2CR2O7. Drag my periodic table back over. I don't know if you guys can see these numbers, but here K is 39.1, so 39.1 times 2, plus 2 chromiums. Here's chromium, it's 52, so 52 times 2, plus 7 oxygens, each at 16. Yeah, so here's potassium, 39.1, chromium at 52, and oxygen at 16. There we go. That gives me 294.2 grams per mole. Is that what you guys got? All right. So I'm not sure that we even necessarily were being careful about this, but the first thing, we're looking for grams, and then step 2, what information do I have? That's right here. Now step 3, let's put it together. And we're going to say, okay, I've got 0.36 moles K2CR2O7 in every 1 liter of the solution. Okay, all right. And then She says we're going to put the 0.05 on top. Liters of solution. Excellent. And then our liters cancel. Awesome. And now we're at moles and I just need grams. So I'm going to use this piece and I'm going to put it on top because I want the grams on the top and the moles on the bottom. So 294.2 grams K2Cr2O7 and every 1 mole K2Cr2O7. When we do that, our moles, potassium dichromate, cancel. We're left with grams, which is just what they asked us for. So 294.2, multiply that by 0.05, multiply that by 0.36, and it looks like 5.30 grams. Is that what you got? Okay. So dimensional analysis should be familiar to you. We've done lots of gram per mole conversions in the past. And really all we are doing now is adding liters and saying, hey, aim for these units or move from these units. And again, as you'll see on a problem like this, students will get stuck on this because the capital M isn't useful. You have to go straight to moles per liter. I'm glad that you did that, Sarah. Okay, perfect. So that's the first thing. And we, as chemists, we use molarity a lot. In fact, it's the basis of what we're going to use when we calculate pH. So we're going to see it again. You're going to need to know it really well, frontwards as we did in section 2 and backwards as we did here in section 3. Next, let's talk about weight percent or volume percent. So this is something that you need to know because you're actually going to see it like at the grocery store all the time. A lot of things are sold as a percent, and understanding what that means is important, right? So for instance, if you go to the grocery store and buy isopropyl alcohol, you can get it in a 30% or a 70% quantity. If you buy hydrogen peroxide, it's probably a 3%. If you are buying skincare products, you might find a toner that is 7% glycolic acid. Or if you're looking at the efficacy of hand sanitizer, don't they tell us it's got to be at least like 65% isopropyl alcohol? So that's where these percentages, where we're going to see that kind of a thing. So here is the key. Percent concentration can be given to mean weight percent, could mean volume percent, or it could be any combination. But the key here is to note that for water, the density is 1 gram per milliliter. So for a solution which contains water, we look at 1 gram and 1 milliliter as being roughly the same. So when we're doing our percentage concentrations, it's either if we're doing weight over weight, or weight over volume, or volume over volume. Any one of these can work, so long as we're using only grams or milliliters. So I can take the grams of the solute divided by the grams of the solution. That would be a weight per weight comparison. I could take the grams of the solute and the milliliters of the solution. That would be a weight per volume comparison. Or I could take the milliliters of the solute and the milliliters of the solution. That's a volume comparison, right? And you just take that fraction comparison, and then to make it a percentage concentration, we multiply it by 100%. Does that make sense? So you can take grams solute divided by milliliters solution, and then multiply the whole thing by 100%. And this gives you a weight, this gives you a percent concentration, and sometimes they'll say W over V to indicate what units that was used to come at that result. Does that make sense? And I could do the same thing here. I can take a milliliters of solute. Like if my liquid is, if I'm looking at alcohol and water, those are both liquids. So it would make more sense to measure the solute in milliliters than grams. Then if I just take the milliliters of each of those, again, divide here, I'm just gonna, that gives me, multiply that by 100%, that gives me my percent concentration, in this case, volume per volume, right? So I'm gonna replace that. And it might say on, you know, whatever you're buying, it'll probably say whether it's weight per volume or volume per volume, how they measured that. And then of course, you can always take your grams solute divided by grams of solution. And you could multiply that by 100% to get your percent concentration in weight per weight. Yes, great question, Sarah. She says, is it always solute over solution, no matter what your units are? And the answer is yes. I think I might have mentioned that up here. Oops, keep going. So solution concentrations, yeah, always amount of solute over amount of solution. So molarity is moles and liters, but the moles is the solute and the liters is the solution. Here we're using grams and milliliters, but it's always the solute over the solution, right? So, all right, here's an example from your, oh, whoops, I'm not supposed to give you the answer. From your lecture notes. You've got 15 grams of glucose in 100 milliliters of solution. Then you would just say, you know, I like doing this. There's my grams of glucose. It's already in grams, so that's nice. And this is in milliliters, so that's nice. I can just stick this one on top of that one, right? Multiply it by 100%. And then I get a 15% glucose solution. Moving on here. If we have, again, alcohol is liquid, so it would make more sense to measure that in milliliters because they're both in milliliters, they're both comparable. Then I can say, okay, 4.5 milliliters alcohol in 6.5 milliliters solution. Multiply that by 100% to see what strength, what concentration that is. So that's a 69.2% alcohol solution. Does that make sense? Oh, such a great question, Sarah. You're asking such good questions. Sarah says, how do your units cancel? Like, what the heck? How come I'm not reporting 69.2 milliliter per milliliter percent, right? Because typically you're not going to say I can cancel the milliliters because these have different identity units, right? And like grams and milliliters don't cancel. So how come they're not in here, right? I've drilled into you guys watching your units constantly. But no, this is because water has a density of 1 gram per milliliter. Then these become comparable units. And they cancel because they are comparable in size, right? So because we are looking at percentages, then you have to have comparable size units. It wouldn't make sense to divide grams by kilograms and then report that as a percent because you're looking at the parts. Percent is parts per 100, right? So here we say, look, if you have a solution with 100 parts and 20 of them are solutes and the grams and the milliliters here are interchangeable because of that density. It's a rough interchangeable, right? Because the density of alcohol is not the same as that of water, but it's still approximate. So you say, if 20 grams in my 100 milliliter solution are solute, and we're going to assume that the other 80 grams is my solvent, right? Then for the total whole, the solution together, 20 grams solute plus 80 grams solvent, then your 20 divided by 100 gives you a 20% concentration. So it's because your milliliters for water can basically be converted to grams to say, if I have a 100 gram solution, which contains 20 grams, say NaCl, plus 80 grams water, right? Then your percentage of your sodium chloride in the water is 20 divided by 100, right? And then because for water, 1 gram is equal to 1 milliliter, we just use these interchangeably. I don't know if that makes sense. Did that make sense to you, Sarah? This is kind of the magic key that makes this work. And it's not perfect for solutions once you put it in, but it's universally accepted. Okay, that's the reason. Okay. All right, so let's do 1 or 2. They're not really hard so long as you remember the formula, right? They're not too hard. So here we go. I actually was really lazy. Look at me be lazy. And I gave you basically the same problems as I did previously for molarity and said, hey, calculate these in percentages instead, right? Well, when we did this one, we had to convert from grams to moles, but now we can leave it in grams because we're doing percent. That's kind of nice. Let's do this one just for fun. How would we solve that guy? Yeah, Nicole and Erica, you guys are exactly right on. You're going to take your liters, convert it to milliliters, and then now that you have grams and milliliters, no big deal, right? So 0.2 liters is 200 milliliters. And then you can 0.2 liters, and you can do the 1,000 milliliters, and 1 liter. That's how we got to 200 milliliters. And so then you just stack them, right? You say, I've got to put grams on top, so 4.75 grams CaNO32. And on the bottom, milliliters, 200 milliliters. And then when I'm done with all of that, I'm going to multiply by 100 to make it a percent. And that all comes out to be 2.375%. Let's do this one down here. Let's do our potassium dichromate. If I've got a 0.360 molar, what do I do with that? Yeah, Sarah, you are exactly right. That is exactly the right thing to do. You say, you see the capital M, and you immediately translate that to say, oh, that's actually moles divided by liters of solution. This is what that is saying. Okay, now I can solve the rest of that problem. But without that, I have nothing to hook on, right? So once I know the number of moles in a liter, now I just have to convert to get me grams in milliliters. How do I do that? I need the molar mass. Hey, I think we did that one already up here, right? K2 right here. So I don't have to calculate that again. I'm gonna drag it down. Okay. So I'm going to convert to grams, make my life easier. 294.2 grams K2Cr2O7, and every 1 mole K2Cr2O7. And my moles cancel. So now I've got grams on top, which is what I need. Now what do I do? Yeah, liters to milliliters, because I need milliliters on the bottom. Like the whole point of percent, I have to have everything in grams or milliliters. Good. So every 1 liter has 1,000 milliliters. And liters cancel. All right, so now that I am in grams per milliliter, I can do the next step, which is to just multiply that by 100%. and then I'll get, I'm like flowing smoothly between, hey, I'm doing dimensional analysis to, okay, now I'm plugging it into a formula. Hopefully that's not too intimidating. Yeah. Oh, times by 100. 10.59%. You guys with me? Okay. And then the next section I've got here, a volume percent. Basically exactly the same, except that I'm telling you, hey, I want you to, oh, come on, come here. I need more. I need more space. Okay, never mind. Just gonna put you over here then. Okay, so now I need volume percent. So how am I going to do volume percent for this guy? Yeah, I need everything in milliliters. So that's already in milliliters, but that is not. So if I have 1,000 milliliters in a liter, I need to make that conversion. So then I can put my original 450 milliliters of my CH3CH2OH and divide that by 1,000 milliliters of solution. Multiply that by 100%, and that equals, right on, Sarah says 45%. Pretty sure that's right. 450 divided by 1,000 times 100. Yeah, 45%. Does that make sense? Okay, I haven't forgot about your question, Zach, but I want to finish kind of this thought or this section. So the next thing we want to talk about is parts per million and parts per billion. These are solution concentration units that we're going to use for very tiny percentages, right? Where if you use a percentage, it would be so small you'd probably have to use scientific notation. So if you're looking at the contamination of arsenic in tap water, for instance, or you're watching Flint, Michigan, the contamination of lead in tap water, or if you're interested in sanitation, you're looking at the contamination of urine in a swimming pool. You might, in those cases, be using units of parts per billion and parts per million. And this is actually not hard to do because it's going to be almost exactly what we have already done. And that is to say, what we did here with concentration in percents is we just calculated parts per 100. The same process is going to be, you'll see in parts per trillion. But so here, previously, we said, look, if I multiply it by 100%, that gives you parts per 100, right? So percent means per 100. So to get the percent, the per 100, I multiplied it by 100. So to get the per million, then instead of multiplying it by 100, I'm going to multiply it by, can you guess? I'm going to multiply it by 1,000,000, right? If multiplying by 100 gives me parts per 100, then multiplying by 1,000,000 is going to give me parts per 1,000,000. So 1,000,000 is 10 raised to the 6th, right? It's going to be 1, that's 10 raised to the 6th. You guys can see that, right? And by that same logic, 1 billion is equals to 10 raised to the 9th. So if I multiply this by 10 to the 6th, instead of getting a percent, I'm going to get parts per million. And it's going to be the same for any of these. So I can multiply, I could still do weight for volume, volume for volume, weight for weight. But generally speaking, it's going to be weight per volume. So I'm, it's going to be the same. But what am I going to multiply this by in order to get parts per billion instead? Going to multiply it by a billion. Right? Basically, I get a very tiny fraction when I compare the two apples to apples units. And then I'm going to multiply that by a very large number. And if I multiply it by 100, I get the percent concentration, percent meaning per 100. If I multiply it by a million instead, I get the per million concentration, and billion gives me parts per billion. And again, you can also do this with weight per weight and volume per volume. Does that make sense? Okay, let's do this one. We've got fluorinated tap water. Fluoridated, okay. Tap water. And to do it, they're putting in, say, 32 milligrams for every 20 kilograms of solution. So what's that concentration going to be? How would we calculate that? Yeah, we need everything in the same thing, right? So we could do grams and milliliters, grams per grams. It looks like they give us both masses, so they have to be the same. And we could take the kilograms to grams and the milligrams to grams, we could take the kilograms to milligrams, so long as they're in the same unit so that they're comparable. But since I said let's do grams and milliliters, then let's do that, right? So let's say we've got 32 milligrams sodium fluoride, and we have 20 kilograms of solution. Then in order to convert these to grams, both of these, we need to remember our metric units, right? And we know that there is 1 milligram, milli means 10 to the negative third, so that's 0.001 grams in a milligram, right? And kilo means 1,000, so there are 1,000 grams in 1 kilogram, right? You could also say 1 gram is 1,000 milligrams. That would give you the same answer. But when we plug this in here, that's going to give us 0.0032 grams of sodium fluoride. And this is going to give us 20,000 grams of solution. And so then to plug this in, we'll say, okay, 0.0032 grams NaF in every 20,000 grams of solution. And then to make this parts per million, we're going to do what? Multiply by 10 raised to the 6. Perfect. Let me just double check this. 32, because Sarah says, is it 0.032 or 0.0032? Okay, so 32 times 0.001. Oh, you're right. I did it in my head and I did it wrong. This is why you do it in your head and then you double check on your calculator. Thank you, Sarah. Double check if I did 32 divided by 1,000, right? Because there's 1,000 milligrams in 1 gram. Yeah, same thing. Good. Good catch. Thank you, Sarah. Okay, so 0.032 divided by 20,000, multiplied that by 1 times 10 to the 6th. Isn't that nice? You didn't really want to say that you had 1.6 times 10 to the negative 6th ratio, right? Or even 1.6 times 10 to the negative 4th percent. It's nice to just say, oh, that's 1.6 parts per million. There. All right, does that make sense? So section 6 on your worksheet looks at parts per million, parts per billion, mass and molarity. Okay, I'll let you guys go, but that's everything on your first in-class activity sheet. So we are gonna follow up on last week's lesson where we were talking about solution concentration units, and we had ended with parts per million and parts per billion, which are related to percent. And if you guys don't remember the formula that we're looking at here, as you have the amount of solute divided by the amount of solution, and it can either be in grams or milliliters or some combination of the two, right? You could have grams over grams, grams over milliliters, milliliters over grams, I guess technically, and milliliters over milliliters, so long as it's grams and milliliters. That divided by that, and that gives you the ratio. And then if you multiply that by 100%, then you get the percent concentration. Percent meaning per, and then cent means 100, so per 100. So you take the fraction, multiply it by 100, you get the ratio per 100, that's the percent. And then if you do the same thing, but instead of multiplying it by 100, if you multiply it by 1,000,000, that gives you the per million concentration, or parts per million. So here we're going to multiply it by, say, 10 raised to the 6th. I'm just going to 10 to the 6th is 1,000,000, and that gives me parts per million. And I can do the same thing if I multiply it by 1,000,000,000, then that gives me parts per billion concentration, right? Technically, I can multiply it by 1,000,000,000,000, and that gives me parts per trillion concentration. Although it's a little hard to get something that dilute. Okay, so let's look at these equations. And for these ones, they're a little bit different than section 5 on the worksheet and section 4 on the worksheet because you're going backwards. So that's kind of just a little bit different. So if we start with this one, instead of, as I did in section 4 and 5, instead of giving you the amount of solute and solution and having you plug it in to find the concentration, now I'm giving you the concentration and I'm asking for the mass that was here, all right? So I'm still gonna take this exact same equation right here, but now I'm going to say, look, this is the percent concentration. I'm gonna like stick this in that spot, okay? And they're telling me the total amount of solution is 500 milliliters, so I can stick this in that spot, right? And now I can solve for the amount of solute, that's the mass of the solute, or grams, right here. I just have to solve. If I use this equation and look at it as a algebraic problem, then I just have to solve for x, and this is my x on top here. Does that make sense? That's x. Okay. All right, so to solve for x, I'm going to divide by 100%, and then I'm going to multiply by 500 milliliters of solution, right? Divide by 100. Oh, that's terrible. Listen to me. Divide by 100%. Divide by 100%. So those cancel. And then I'm going to multiply by 500 milliliters of solution. Stick it right there. Move it over. All right, so that gets removed. And what I'm left with is 0.5 divided by 100 times 500 gives me 2.5. And again, this is either in grams or milliliters. So they're asking for mass, so I'm just going to report that in grams. That actually makes more sense because that's typically a solid. 2.5 grams, H3BO3. Does this make sense to y'all? Okay, so again, for this one, we're using grams and milliliters interchangeably because in solution for water, the density of pure water is 1 gram. So for water, 1 gram is equal to 1 milliliter if it's pure water, right? Now that is not always 100% true for solutions, especially really concentrated solutions, but it's still an approximation that we use. And especially it really works with these very low concentrations, which have mostly pure water in them. So because the density of water is 1 gram per milliliter, then we look at them as being equal. So it's like they cancel almost. Yeah, when we do these, so long as we're in grams and milliliters, we're gonna drop those units and then we're just gonna report this as percent or parts per million or parts per billion. And we don't, in this product, we don't say, other than saying that it was measured this way, right? Which it does, it says right here, by the way, this was measured as weight per volume. So you know that they used grams on the top and milliliters on the bottom when they were measuring that. Okay, so let's look at, these other ones are also kind of tricky. Let's see, which of the following solutions is more concentrated? We have a 5% weight per volume and a 0.5 molar KCl solution. Well, what's hard about this problem is that you're given totally different units, but you're also not given any information about like how much of the solution I have, right? You're just given concentration. And in order to determine which one is more concentrated, we have to compare apples to apples. Right now it's apples to oranges, right? So I can either choose to convert molarity to percent and then compare the 2%, or I could convert percentages to molarity and then compare the 2 molarities. And either one of those is gonna be totally fine. Do you guys have a particular preference as to which method I should use to solve this problem? Sarah says convert to molarity. Okay. We'll do that then. We're going to convert a 5% solution to molarity. Okay, so we're going to remember that this is what percent means. And if I can get from my 5% weight per volume back to, my fraction of amount over amount, then I can convert this fraction, which would have grams over milliliters, I can convert that to units of molarity. If that makes sense. Does that kind of make sense? This is what we have so far. We know that it's 5% and we know that this is the formula for calculating percent. So whatever this formula was, calculated this number. So next step, I'm going to divide both by 100%. Whoops. Oh. Let's try that again. Divide that by 100%. And these cancel. Okay. So the amount of solute divided by the amount of solution is 5 divided by 100 is 0.05. Okay. So that is equal to 0.05, and this was weight per volume, and that's amount over amount, and I have to use grams and milliliters. So what that really means is 0.05 grams of solute divided by 1 milliliter of solution. Do you guys see what I did there? That 0.05 has to be the same as 0.05 divided by 1. So here, I don't know how much solution I have. I just know that for every 1 milliliter of solution, that's the number of grams. So I'm just going to kind of work with 1 milliliter of solution and go from there. Okay. So, I don't know how much there is, but in every 1 milliliter, I know there's this much. Yes. Okay. Erica and Sarah, you guys are totally getting it. You see where I'm going with this. Okay. We have to go from percentage to molarity. And you guys know molarity is, that capital M is useless. What it really means is moles divided by liters. Okay, so to convert this to molarity, I have to convert this from grams and milliliters to moles and liters. And you can totally do that. You know what you're doing on that front. But because this one gives you grams and milliliters, this is what we've got to work with. And now we're just going to move that direction and say, okay, what I really need is liters. So how do I go from milliliters to liters? Zach's totally right. We could use 1,000 milliliters in 1 liter of that solution. Yes. If we do that, the milliliters of solution cancel, and we're left with liters of the solution on the bottom, which is exactly what I need for my target units. All right, we're happy about that. Now we need moles on top and we have grams on top. And this is kind of funny because we have done all this work without even asking ourselves, what's the solute, right? We don't even care. We're like, this concentration is this. I don't know what the concentration is about, but it's this. But now we have to actually go back and say, okay, if I want to go from grams to moles, I need the molar mass. And to find the molar mass, I have to know what I'm even talking about. All right, back to the problem. Oh, it's KCl. I didn't need it, so I didn't remember it. Okay, but if you look up on the periodic table, chlorine has a mass of 35.45 approximately, and potassium has a mass of about 39.1, I believe. And so Sarah has calculated that, and that looks about right, to say 74.55 grams per mole of KCl. Sarah always says AMU, which is the number of atomic mass units in a molecule, right? But it's the same as the number of grams in a mole. So am I going to put that number on top or on bottom? On bottom, right? The 1 mole I need to go on top, and then the 74.55 grams KCl on the bottom. Okay, KCl being my solute, right? So my grams of solute, which was KCl, cancels. And now I'm left with moles divided by liters, and that's molarity. So it will be comparable to this guy. We're comparing apples to apples. So 0.05 times 1,000 divided by 74.55 gives me 0.671 molarity KCl. Does that make sense to you guys? Now we just compare it here. And we see, oh, 0.671 is larger than 0.5. So 5% in this case is more concentrated, actually. That's not going to be true in every case, because it depends largely on that molar mass unit, right? If your solute was really, really heavy, then this would be a smaller number. So in this case, yes, the 5% is more concentrated, because when I convert it to molarity, it's 0.671, and 0.671 is greater than 0.5. Okay, let's look at one of these two on the right-hand side. They're basically the same, so I'll only do one of them. And I'll let you guys work from there. Do you guys have an opinion as to which one you want to do? Arsenic or beryllium? Both highly toxic species. Okay, we'll do arsenic. All right, so we're gonna convert, they want us to convert from parts per million to percent by mass, and also from parts per million to molarity. So this is also tricky. We're going a little bit backwards, but from what we know, we're going to use this equation right here. And we were given that it's actually 0.010 parts per million. That's my actual concentration. Okay. So I can divide this by 10 to the 6th. Divide that by 10 to the 6th. So that these will cancel, right? And I get 0.010 divided by 1 times 10 to the 6th. Well, that's not helpful. Okay, it gives me a value of 1 times 10 to the negative 8th. Okay, so I have solved. This is equal to 1 times 10 to the negative 8th. Okay, now that's my amount of solute divided by amount of solution, and it tells me this is probably weight per mass. So that is essentially saying this is 1 times 10 to the negative 8th grams, and just a tiny, that's 10 nanograms, right? So such a tiny amount. And in this case, it is arsenic, right? That's my solute in every, because it's volume on the bottom, 1 milliliter solution. And I put that in there because I'm using this formula and it always has to be in grams and milliliters. So I'm putting grams on top, milliliters on the bottom. Does that make sense? Now I can take this and plug it into my percent concentration formula and say, look, if I multiply it by 100%, I'll get my percentage concentration. Because it's the same ratio. So, all right, 1 times 10 to the negative 8th, multiply that by 100%. Whoops. Yes, okay. That gives me 1 times 10 to the negative 6th. You can kind of see why we use parts per million, because you're like, whoa, I don't want to use percentages. It's such a tiny number. I don't like exponents. It's nice to just have a value that I don't have to worry about scientific notation in, okay? But that's the percentage. Does that make sense how I got there? Okay. The next step is to take it to molarity, which is going to be basically exactly the same thing that we did down here, right? If I know that fraction in grams and milliliters, then I'm going to be able to convert it to moles and liters, and that's not a huge challenge for me. Okay, so I have 1 times 10 to the negative 8th grams of arsenic in every 1 milliliter of solution. And I just have to convert that to liters. So I'm going to do 1,000 milliliters on the top and 1 liter of solution. And then I'm going to say, I need the molar mass. Help me out here, guys. Sarah is prepared. Arsenic has a molar mass of 74.92 grams per mole. I believe you. So I'm going to put 1 mole of arsenic on top, 74.92 grams of arsenic on the bottom. Do that so my grams of arsenic will cancel right here. And I'll be left with moles on the top and liters on the bottom. Okay, so if I have 1 times 10 to the negative 8, and I multiply that by 1,000, and then divide that by 74.92, this gives me a molarity of 1.33 times 10 to the negative 7. All right, just move this guy up. Right there. Oh, and I forgot my units. That's going to be molarity arsenic. Does that make sense? Does that help you? We got kind of cut off on this last Thursday, so it's nice to cover it again.